Look at this simple maths problem. It's just slop, right? Your standard inane clickbait. Well, no. It actually involves some of the most interesting maths developed over the last 100 years. Elliptic curves. Just try solving it. It seems simple enough. Plug in some positive whole values until the sum equals 4. But if you try that, you'll be out of luck. If you're dedicated, maybe even try a computer search. But still nothing, and you'd probably start thinking that it's just not possible. But it is possible. With a catch, and a big one. I'll show you the simplest solution now. Apple equals 4373 612 677. Keeps going and going and going and going. Banana, even bigger. And pineapple. And this is the smallest possible answer. How can it be that such a simple equation has such a crazy solution? And how to find it? Well, I'll show you in this video. And you only need to know basic algebra, addition, subtraction, multiplication and division. Yes, a very cunning trick will be needed, but no advanced theory. And once you've seen the trick, maybe then you'll also understand the magic of elliptic curves. Anyway, the original meme has been floating around the internet for a few years now, and it was devised by actual proper mathematicians, sadistic mathematicians maybe, but proper ones, and cleverly disguised as your usual silly little meme. Here's some other versions I've seen, sometimes with different objects for the numbers, sometimes with a different number on the right, but always with this claim that 95% or so of people cannot solve it, which is hopelessly optimistic, by the way. There's no chance that 5% of people can solve this equation. Well, unless they've watched this video. Okay, so what to do with this? Considering the hugeness of the smallest solution, it should go without saying that a brute force search is not going to give you a solution. These numbers have around 80 digits. If you were to just iterate through possible values for x and y and solve for z, check if it's a positive whole number, then you're not going to come across any solutions until this many attempts. A number with 159 digits, and I don't even know how to get across how unfathomably huge this is. Even if you had a computer with every atom in the observable universe searching quintillions of solutions per second, you won't get anywhere close before all the stars have blinked out of existence. So let's not do that. Let's look at the equation and forget fruit, use x, y and z like proper grown-ups. The first thing, the left side does not change if the values are scaled. Multiply x, y and z by the same value. The scaling in the denominator and numerator cancel. Makes no difference. So the actual values don't matter. It's just the ratio that we care about. Written like this, with colons. The ratio 1:5, for example, is the same as the ratio 2:4:10. So the original question isn't really about integer solutions because they can always be scaled. Any positive rational solution will work. You just then scale them up by a common denominator. But what does this equation really look like? To get a complete view, I'm thinking about all solutions for the moment, not just positive ones. Well, an equation in 3 variables will give a surface in 3D space. But that's overcomplicating it, because here only the ratios matter, and the set of points in space with any fixed ratio is a line through the origin. So the solution will be a collection of these lines. And to visualize the solutions, it's only necessary to consider one point on each line, like where z equals 1. Then it's an equation in x and y, a curve in the plane. And solutions can always be scaled, so z equals 1 and is on the curve. Well, except for those with z 0, they can't be scaled to 1, but they show up as limits at infinity, or asymptotes to the curve. Alternatively, scale so that the vector xyz is of unit size. This includes all possible solutions as a curve on the unit sphere. But now, opposite points on the sphere are the same solution, the same ratio. They've just been scaled by -1. But however you want to represent these solutions, lines through the origin, the plane at z equals 1 plus points at infinity, or the sphere with opposite points identified. This is known mathematically as the projective plane. And you don't actually need to be able to visualize the solutions to solve the equation. It's just algebra after all. but it's pretty nice to see what we're dealing with, especially here in a YouTube video, so you won't have to watch me all the time. Okay, after noting that only the ratios matter, so this is a question about projective space, the next thing we can do is remove these divisions in the equation. Just multiply by denominators. This removes the possibility of division by 0, and we get this, a cubic, a homogeneous one, where every term in the expression has degree 3 in x, y and z. Or if you want to scale, so z is 1, a cubic in x and y. Either way, this is a cubic curve. Now at this point a mathematician might just say, oh, it's an elliptic curve. And there's a lot of theory about this, and they might even do something like reach for some software which has elliptic curve theory built in, like Sage Math, which will be able to solve it, and they'll say, well, we're done, we've solved the equation. But no, I'm not going to do that. This is not a tutorial on Sage Math or other software. What I want to do is solve this just using standard methods: addition, multiplication, division, basic algebra. Well, here's a neat algebraic fact about cubic curves. Any line passing through 2 rational points will also pass through a 3rd rational point, counting multiplicity of the intersection. Just consider rational points P and Q on the curve, and the line passing through them is a linear combination of these, SP plus TQ, in the plane where Z equals 1, and then S plus T is 1, so this is 1 minus TP plus TQ, the familiar equation for the line through 2 points. But in projective space, we scale by an arbitrary factor, so there's no need to restrict this plane. Anyway, plug into our homogeneous cubic defining the curve. We get a cubic in S and T. There's S cubed terms and S squared T, ST squared and T cubed terms. But here's the neat bit. If T equals 0, then this point is a multiple of P. So it's on the curve and it vanishes. So the coefficient of S cubed is 0. And if S is 0, then it's a multiple of Q. So it vanishes again. The same thing. So there's no T cubed term either. All we have is S squared T and ST squared. So our cubic factors into S times T times a linear term. And setting each of these to 0 gives 3 points on the curve. Setting S or T to 0 gives the 2 original points back, P and Q, but there's a 3rd factor, and this gives another point on the curve, where S equals C and T is minus B. So any 2 rational points gives us a new point by this chord construction. But what if P and Q are equal? So they're the same point. Can we still construct another point on the curve? Yes, we can. Suppose Q approaches P. Then the chord joining them approaches the tangent line to the curve. Pretty standard stuff. And if we want our chord operation to be continuous, then we must use the tangent line. But let's see this in an example. I'll start with this simpler cubic, x cubed plus y cubed equals z cubed, and plot the curve on the plane z equals 1. Okay, you might recognise this one from Fermat's last theorem. There's no non-zero integer solutions. So let's modify it. X cubed plus y cubed equals 7z cubed. And I choose 7 here for a reason. It's the difference of 2 cubes. 2 cubed plus minus 1 cubed is 7 times 1 cubed. That's 1 point on the curve. Nice. But is there a positive integer solution? Well, let's take the tangent at our point. It intersects at another positive point. So let's write it out algebraically. The derivative at our point with respect to x, y and z, this is 3x squared, 3y squared and minus 7 times 3z squared. Factoring out the 3, this comes to 1, 4 and minus 7. So the tangent line is orthogonal to this. So we can take the direction as 4 minus 1, 0. We take s times p plus t times v, that's the tangent line, and apply our cubic. The coefficient of s cubed is this value of p, 0, and the coefficient of s squared t is the derivative of f along direction v, 0 again, because it's a tangent. The st squared term, expanding out the cubes, we get 3 times minus 1 times 4 squared plus 2 times minus 1 squared, or 3 times 14. The coefficient of t cubed is the cubic value at v, or 4 cubed plus minus 1 cubed. 21 t squared times 3t minus 2s. That's a double root at t equals 0, which it has to be because the line is tangent to p, and another root at s equals 3 and t equals 2. This comes to 5, 4 and 3. So that point is on the curve. 4 cubed plus 5 cubed equals 7 times 3 cubed. Magic! You can check it, it's all correct. But we managed to jump straight to this solution, no explicit searching, just algebra. And we can keep going like this. If we take the chord between our 2 points, we just go back to the original point. So let's switch x and y here, reflect that point. It's still on the curve, and now we take the chord with p. We get a new point, not positive, but take the tangent. And we do get a new positive point. And you can work it out, easy enough, but the numbers are getting a bit big. So here's what you get. Instead of taking chords, why not take the tangent again? And the chord of this with the earlier point. A positive solution. In fact, the exact same positive solution. Or maybe take tangents yet again. And then take the chord. We get the same solution again. Or take the chord between p and our second solution. Gives a third, even bigger solution. We could keep going like this, generating ever more positive solutions, which just keep growing bigger and bigger at quite an alarming rate. But there's lots and lots of ways in which we can take combinations of chords and tangents, giving a massive mess of solutions. But we saw many different constructions give the same answer. So there seems to be something going on here, right? Why should seemingly different constructions with different in-between points so often give the same answer? Sounds like something is happening underneath, some symmetry or structure. And that's exactly right, there is, and I'll show you. But first, back to the fruit. So back to the fruity meme. Let's multiply by denominators to get a cubic. It's a little bit messy now, so I'll make a substitution. Let u, v and w be the denominators, and I'll write the whole thing in terms of these. As the sum of u, v and w is twice the sum of x, y and z, we can just subtract u, v and w from this to invert the substitution to get x, y and z in terms of u, v and w. Anyway, this curve is a little bit simpler, rearranging uv times u plus v plus similar terms equals 11 uvw. You don't need to make this substitution, but it seems a little bit simpler to me. And from the plot you can see that the curve actually breaks down into 2 bits. This unbounded section, well unbounded if plotted in the UV plane, and this bounded closed loop, or bounded oval. Also the reflection of this closed loop, but remember that opposite points on the sphere represent the same ratios, so the opposite loop is really the same one. And let's fill in the region which corresponds to positive x, y and z. We can see that only the bounded closed loop intersects this region. To solve the puzzle, we need points in here. Anyway, let's find simple solutions to start. Setting u equal to 0, the curve is vw times v plus w equals 0. An obvious solution is v equals 0. So the point 0, 0, w is on the curve, or 0, 0, 1 up to scaling, and is symmetric. So we've got points 1, 0, 0, 0, 1, 0, and 0, 0, 1, all on the curve. I'll call these P1, P2, and P3. But there's more. We can take V plus W equal to 0. Up to scaling, this is 0, 1, minus 1, and by symmetry, 1, 0, minus 1, and 1, minus 1, 0. They're also on the curve. And I'll call these O1, O2, and O3. But what if we take chords and tangents? Can we find new solutions? Well, looking at the difference between P1 and P2, This is 1, minus 1, 0, or O3. So they all lie in a line. The chord through P1 and P2 gives O3. By symmetry, under exchanging 1, 2 and 3, Pi, Pj gives OK. Whenever ij and k are 1, 2, 3 in some order. So Pi, OK and Pj lie in a line, and in the same way, Pi and OK chord construction gives Pj. No new points found so far. And the difference of O1 and O2 gives O3. They lie in a line, so O1, O2 gives O3, or as before, OI, OJ gives OK. Next, if UVW is any point on the curve, then by symmetry, UWV is also on it. And the difference of these is a multiple of O1. So they lie on the line, and applying O1 with the chord construction exchanges V and W. At least it does, if these are all distinct points on the line. But by continuity, it's always the case that applying O1 exchanges V and W. So let's apply O1 to itself, the tangent construction, and it gives O1 back, so the tangent construction from OI gives itself. The tangent line intersects with multiplicity 3, and applying O1 to P1, it gives P1. So these lie in a line. Listing in a different order, the tangent of P1 gives O1. There's no new points. These 6 special points are all closed under chord and tangent constructions. It's not helping. We're going to have to resort to a brute force search. But we don't need to search for positive solutions, which we saw were ginormous. There's no way we'll find those. But just a small, non-positive solution maybe, and that should be enough to get going with our chord and tangent business. So here we go. I wrote this simple Python code which searches for u, v and w solving the equation. By flipping signs, we only need positive u, and I'm iterating over u and v less than u and w less than v in absolute values. It could be made more efficient, but let's try this, just running for small values of u. And straight away we have a solution. u, v, w equals 10, 3, 2. This is not actually positive for x, y and z. In fact, it gives x equals minus 5, y equals 9 and z equals 11. But plug it into the original equation and you can check that it works, which is pretty nice. So let's use this along with the chord and tangent method to find new solutions. But I'm not doing that by hand. I mean, no way. I'm not doing algebraic manipulations of 80-digit numbers by hand. But luckily, Python handles these with no trouble. So I wrote some Python code again. Now the point class here is used to represent points on our curve. It's just inherited from tuples, so it's a tuple of 3 integers. And it automatically checks that your tuple is on the curve. So if your point is on the curve, fine. If it isn't, then an exception. Anyway, our point, 10, 3, 2, that's on the curve. Good. Next, I wrote code to do the chord construction. At a point u0, u1, u2, the cubic can be rearranged as sum ui uj squared minus 11 u0, u1, u2. And evaluating this at point su plus tv, we get these terms for the coefficients of s squared t and st squared. So the chord construction gives this point w equal to qu minus pv. Then, well, I factor out the greatest common factor, but that's just to put them in a standard form. And if the 2 points are the same, then I do this. I do the tangent construction instead. So this is the gradient of the cubic. Then the direction of the tangent curve is orthogonal to this, which I do by taking the cross product of g and the point u. And applying the cubic at su plus tv, we get these terms for the coefficients of st squared and t cubed. So the tangent line intersects at this point. And this defines a multiplication operator on the point class to be the chord and tangent construction. For example, P1 times P2. We get O3, or P1 times P1. That's O1, just as we worked out before. Anyway, starting from point Q on the curve, we can try applying this to find new points. And in fact, I wrote this short function. Pass in some points, a list of points, and then it will apply the chord and tangent construction between every pair of them, and then it adds these to the list if they are new points, and then it repeats until you get a positive solution. Now there's going to be a lot of repetition here. The same points may be constructed over and over again, so it's not very efficient, but it's simple. So let's try starting from points P1 and Q. And running this, done. We have a solution after repeating just 3 times. Hurrah! The fruit problem is solved. But what was the construction that actually worked here? Checking the output, I see it did this. Q3 is equal to P1 times Q. Q4 is equal to Q times Q. Q7 equals Q3 times Q3. Q9 is equal to Q4 times Q3. Q15 equals Q7 times Q7. Q17 is Q9 times Q7. And then finally, Q33 is Q17 times Q15. And we got the solution. So that was 7 separate chord and tangent constructions to get the answer. But it can be done in different ways. Playing around with it myself, I see it can actually be done in 5 steps. We do this. R1 equals P1 times Q. Then we do R2 equals Q times Q. Then R3 is R2 times R2. R4 is R3 times R3. And then finally, our solution is given by R4 times R1. But what's going on? How did different constructions give the same result? And was this guaranteed to work? Well, cubic curves like this are also called elliptic curves, and they may or may not have infinitely many rational points, but either way it's always possible to generate all rational points using the chord and tangent method, starting from a finite set. This is called Mordel's theorem. It was proven in 1922 and is one of the most celebrated results of elliptic curve theory. But which finite set? Are the points that we found enough to construct every single rational point on the curve? And were we always guaranteed at the outset to find one with positive x, y and z values? Well, the answer is yes, and yes. Okay, now we've solved the fruit problem, the real fun can start. Time to reveal the underlying structure. For any point P on the curve, I'll define minus P by switching the last 2 components. It's still on the curve by symmetry, and it's the same as taking the chord construction with O1. And the sum of 2 points will be defined as the negative of the chord construction. That is the chord or tangent construction with the last 2 components switched. Now here's the structure. This is a group, with O1 as the identity. It might sound like a small statement, but really it makes the whole thing fit into place. It means that when we add points on the curve, it doesn't matter how we group them. It doesn't matter where the brackets go. P plus Q plus R equals P plus Q plus R. So the order in which we do the chord and tangent constructions does not matter. So when I looked for solutions by combining P1 and Q, all that mattered was the number of P1s and Qs in the sum, and P1 added to itself is the identity, O1. So 2P1 is the identity O1, so cancelling an even multiple of P1, all points constructed are like n lots of Q or n lots of Q plus P1. That's it. So we just need to compute multiples of Q in order, and check if NQ or NQ plus P1 have positive x, y and z. And the graphic helps a lot to see what's happening. Any line intersecting the bounded oval component must intersect it twice, exactly twice. So using curve and tangent construction starting only with points on the unbounded section, it can never give a point on the bounded oval. We were never going to find any solutions to the fruit problem with the simple points P1, P2, P3 and so on. But the point Q that we found, this was on the oval, which is exactly what was needed. We keep adding Q, then the points alternate between the bounded oval and the unbounded component. So only odd multiples will be on the oval. Let's check this. Q, Q plus P1, now 3Q, 3Q plus P1, 5Q, 5Q plus P1, 7q, 7q plus p1, 9q, 9q plus p1. Done! We have the solution, 9q plus p1, and as you can see, as we kept adding 2q, the point kept bouncing around the bounded oval until we hit the region with positive x, y, z. Now you might ask, why am I only adding p1 to multiples of q? What about p2, p3, o2, o3? Well, we can also try those, but it only permutes the order of the components of the point. It's not going to help find positive solutions any faster. Anyway, even without trying, our points had to eventually hit this positive region. Our rational points will hit any region on the curve. They are dense. Okay, but how do we know that? Maybe multiples of q will eventually start repeating over a finite set. Well, I mean, I just ran with it and it worked. I found a solution. But there's a lot of advanced theory of elliptic curves which helps find generators for the rational points and software that has this theory built in, like SageMath. In fact, I think most mathematicians trying to solve this problem would just use software like this. But without using some black box software to tell us the answer, how do we know that multiples of q really give an infinite sequence of rational points without repeating? Well, with some black magic. Let me explain. Points whose multiples just repeat over a finite set, these are called torsion points. Same as having some multiple of the point equal to 0, or O1. And these torsion points form a group. Adding them together just gives more torsion points. And in fact, there's only finitely many rational torsion points on any elliptic curve. And we found 6 of them already, the pi and oi, and you can check. 2p2 or p2 plus p2 is O3, 3p2 is p2 plus O3 or p1. So multiples of p2 just cycle through our 6 special points over and over with period 6. And this is a cyclic group of size 6, same as the integers modulo 6. Well, here's the black magic. Mazur's theorem says that the group of rational torsion points can only be one of 15 possibilities. It can be cyclic, of size n, for n up to 10, or n equal to 12, or it can be the product of a cyclic group of size 2n, and the group with 2 elements for n up to 4. But as soon as we found our point q and we saw that q plus q was not one of our special points, then we know it's not torsion, because adding q or 2q to our 6 points gives 18 torsion points. Impossible. So Mazur's theorem rules this out. So multiples of q keep giving new points on the curve until eventually we must find one with positive x, y, and z. Amazing. We did not need to know all this to solve the food problem. We solved it with just simple algebra, but Mazur's theorem seems like some kind of magic, some inside knowledge that helps us solve so many problems. The theory of elliptic curves has many amazing results like this, like Mazur's theorem, which are just so awe-inspiring in their power and beauty. So that's about it from me, but before I go, we found a solution to the food problem, but how do we know it's the smallest solution? That's what I claimed right at the start of this video. Well, with more elliptic curve magic, of course. The height of a rational point on the curve, after taking out common factors, can be defined as the maximum of the 3 coordinates. And as you add points, this grows very, very quickly. N times q will have height growing exponentially in n squared. The logarithm of this height can be bounded by a quadratic in n. In fact, within a bounded amount, it is a quadratic form and grows like n squared. And this can be used to bound the height and shows that bigger and bigger multiples of q just give even bigger numbers than the one we found. In fact, Christopher Long, Octonian on Twitter, he's written SageMath code to find the minimum solutions to a whole set of problems like this, where the number on the right hand side can be different positive integers. Anyway, that's it from me. Please like and subscribe. I'll be back soon with some less fruity videos, almost surely.
Oh yeah, I'm almost sure.